Hello, this is Greg Wagner for CIS or CSCV 471 Artificial Intelligence at the University of Arizona. Today's class is lesson 5, which is going to go over adversarial search and gameplay. And so basically, it's going to be how do you, if you're competing against another competitor or something, how would you predict the kind of moves they're going to do? So in the Russell Norvig book, this covers sections 5.1 through 5.4. So the initial model we have for a search agent was we have a sensor taking the environment and the agent does something, then an actuator moves it. For a game plane agent, the environment's going to be modified by another agent. And so you have to adjust to those modifications. That scene's always changing based on the moves that someone makes. And so the idea is, ideally for AI, you'd have a perfect two-player game. We have two players, max and min take turns. And for the max player, you're trying to increase the basically whatever the score cost function, and the min is trying to get it as low as possible. But other than that, it's basically the same as a search space. You have the state space, initial space, successor function, terminal test, and then you have a score function, which is what the max is trying to maximize and the min is trying to minimize. And you have a perfect knowledge of the states, so there's no uncertainty in the successor function. You know what the next function is going to do, but you may not know what the adversary is going to do. So to give an example of a two-state problem, you'd have Grundy's game. Basically what you're trying to do is you have a stack of 7 coins, and then you have a state, which is the set of stacks, and you have a successor function. And so what you're going to do is you're going to break one stack of coins into 2 unequal stacks. So in this case, what you would do is you have one stack here, so you try to take, you break this stack and break it into 2. And then so the game wins is whatever is the last person to have all the stacks contain 1 or 2 coins. And so the terminal state is a win for max if it was generated by max and a loss otherwise. So basically, if you have 1 or 2 coins on the stack, so you try to manipulate the other person so you have a certain number of stacks per game. So how this would work out in an adversarial type of tree is you initially start with the stack of 7, and then the next person moves so that the possible moves they can have, so they can have a stack of 1, 2, or 3. And so those are the 3 different moves they can do, and then after that, from this stack, you can either make it to 1 and 1, or you can have it kind of have these interconnected trees. And so the ideal path would be, so you're going to win if you follow this path, or lose if you follow this path, and the other person's going to win if you follow this path. So you're trying to do is force the other team to have a stack of 2 or 1. Now for TicTacToe, which is what we're going to do for the assignment for this class, for this over this module, is you have your initial state. So you have the initial state, then you have the first move, and then you follow the moves down from there. So in this case, ideally you'd want to get the best position by putting your X in the middle, and then the O person would have these initial states, and then from that position you can have maybe 4 different states that would benefit you. And then in this case you'd have, so they follow you assume that the adversary, so they're going to follow this path, so they're going to go okay here. So not only can you block this path, but you can also get the best performance. And so since we do not know what the adversary is going to do ahead of time, we have what's called uncertainty action model, which means, okay, how can I want to get from this initial state to this state? What would the adversary need to do for me to get between those states? So what you're doing is you're kind of picking the terminal state you want to get to and figure out what the opponent needs to do for you to get back to that state. And so what you want to do is make the best decision assuming the worst case outcome. So what you want to do is come up with a decision based on what happens if the opponent does something smart. If the opponent does something stupid, you basically can get them into a corner, but if they do something smart, you have to be able to account for that. And so to evaluate the function, you have E of S, and if E of S is positive infinity, S is a win for max. So basically, it's the max value you can get. If E of S is minus, it's a pin for min, so it's a win for your opponent. And then E of S is a measure of how favorable it is for max. So if the value is 0, it's neutral. If it's greater than 0, it's considered favorable for max. If it's less than 0, it's considered favorable for min. And so for tic-tac-toe, we're going to give the score of E of S as the number of rows, columns, and diagonals open to max, minus the number of rows, columns, and diagonals open for min. So in this case, the initial state is neutral because everyone has an equal number of states. Now in this case, we have X, O. So X has basically the number of ways open to it is 1, 2, 3, 4, 5, 6. This is not open to it because you can't win this way. This is not a good move. Whereas 0 places that can go and still win are 1, 2. Can't put any spaces here. 3, 4, and this would not help it. So it has an advantage of 6 to 2. So when you're doing the assignment, you're going to usually use the scoring metric. And so what you want to do is find the places where you can actually still win. And that's kind of the logic you need to put into this. So now we're in the next move here. To kind of give you another example. So this one, while it looks obvious that 0 is going to win, by our measurement, it's actually neutral because for X, that's max, the positions where we can still win are, let's see, 1, 2, 3. So it can still win in these positions. It really can't win in these two positions. Whereas O's can still win by putting one here, here, or here. So it's considered a neutral position, but actually, if you look at it, it's beneficial. But it's kind of just an example that it's beneficial for the min, or the O's. So let's say we have the initial state, and you want to have tic-tac-toe with horizontal 2. So in this case, we have X here, and so all the winning positions for X for the O's could be 1, 2, 3, 4, 5. If you put the X here, the win positions can be 1, 2, 3, 4, 5. And for this case, the win positions you have for O are just 2. So this is clearly a more beneficial position for it. And so you can look at all the different scores and putting the X in the middle. If you've ever played tic-tac-toe before, it's obvious that you want to put a position in the middle here. And then so when we're doing, you can see that for the max, for the beta, what you want to do is put the lowest position for this value. So what's the least beneficial one? So we have the lowest score here is going to be -1. The lowest score for this one is going to be -2. So this position's bad, this position's bad, but this position has the lowest score of 1. So again, what we're trying to do is find the position that has the least. You want to, when you're calculating the score for this level, this will be called the beta score, is the minimum of the lower level. And so this one's -1, -2. So you see, this is the best position. And if you were playing, you'd want to put your marker here. And then you move up, and you find then you find the max of this row, and this would put you at 1 up here. And so this is the move you'd want to do. And so again, for this example, if you're in this position, you get a score of 1 here. So this would be your next move, but this is considered the alpha row, or the alpha column, or the min row. you get the minimum of the next level and score the one above it. So 1's the lowest level here, 0 is the lowest one here, 1's the lowest one here, and 0 is the lowest one here. So where would you want to move? You'd want to put your marker either here or here. And you can see it's obvious. If you put one there, you have basically multiple paths to win, whereas if you put it here, you basically only have one way to win. And so then you would move up the max of this row to the next level. Now I'll tell you what path you want to go in. So we're going to pick this path. And so for the min-max procedure, you expand the game of the trees uniformly from the current state, so wherever you're at that current moment. Compute the evaluation function at every leaf of a tree. So you basically, you go down the layers and figure out what's the best performance, and then back up. The max node gets the maximum of the elevation of the successor. The min node, so if you look here, the min node is going to be this row. This one gets the minimum, and the max node is the blue ones. It gets the maximum, or the green ones. And so the max node gets the maximum of the evaluation of the successors. The min node gets the minimum of the evaluation of the successors. And then you select the move towards the min node that has the maximum backed up values. And what I wanted to point out here is the horizontal of the procedure. That's the horizontal of the procedure. You want to limit the size of need to limit the size of the tree or return a decision within an allowed time. So the main thing is one of the parameters you need to set is how many different steps you can say. For like a simulation, say like you're doing like war games or like flight simulation or something like that, or even car driving, you're basically limited by physics. But you kind of will kind of cheat that. Like the TicTacToe, you're actually limited by only a set number of moves. And so for playing the game, you're going to repeat until you win, lose, or draw. You're going to select the move using the min-max procedure, execute the move, and then observe what the min's move is going to be, and then you're going to move on from there. So in a bigger state, what we also need to do is prune. So basically, we're only going to go down paths that, so we see this huge tree, but it grows exponentially. What we want to do is avoid paths where we get poor performance. And what we'll go over now is how would you do that. So we're going to use the alpha-beta procedure. So generate a game of depth of h, so in a depth-first manner. So we're going to basically figure out how many steps we're going to go down, and then we're going to back up, estimate the alpha and beta values of the evaluation functions whenever possible. So we're going to score each of the scenarios and then back them up. And we're going to prune the branches that cannot lead to changing the final decisions. So we're basically going to prune branches that don't have really bad outcomes. And so, for example, if we have this scenario here, and we can get a score of 1. In this case, the beta value is 1. So this is the minimum score possible. The beta value, and then so the beta value is the minimum score for the min level. So the minimum score of a successor. And then so in this case now it moves to 0. And then now it moves to 1. So it's going to be still the minimum because it's still 0. And then it's still 1. So the beta doesn't change unless the value, as the value goes down. It can never increase. And then finally we get a step where they put 0, which is actually a really good beneficial position here. And so it becomes -1. And then we'll look at the next path. So, and then that value gets passed up. So this, remember, this is going to be the maximum value from the min row up at the max row. And so the alpha, again, is the maximum of the lower bound that can be backed up. And then this value can never decrease. So it will only go up from -1. So now we're going to move on to this position. And we see that the beta here is going to become -1. And so we're basically not going to continue down this path because with the beta being -1, we really can't do much better. And so, since this can increase, we're basically just going to stick down this path and ignore this path. And this search cannot be discontinued below any min node that's less than or equal to. So basically, if the min node is less than or equal to the max node, we're not going to continue. So in a big example, so this one has a depth of 1, 2, 3, 4, 5, and we have the scores of all at the lower levels here. So we're going to work our way up this. So at this level it's 0 because the min here is 0, and then that value is passed up as 0. So this path is kind of the optimal path that we want to travel on, but we're still going to pass up from the beta level to the alpha level of 0, and then that value is going to be passed all the way up. Now we're going to look at this one, and so this one, the minimum 0, but remember this value, the green level, the alpha level, only cannot decrease, it only could increase. So it's -3, so it's going to still stay at 0. So remember, this is the min row, so we get the min of the successors. This is the green are the max row, so it's going to get the max of the success of its successor, so it's still 0. And so we see 0 is greater than 3, so we're going to keep that one, and it's going to be passed up to the next level. Now we're going on the next path. We see 3 for this particular case. And so in this instance, since we're looking for the minimum, we're still going to stick with this value. However, notice how these are not going to be searched those because there's no values in here that are greater than, we basically saying, okay, we're not increasing here, so we know that we can't do basically any worse. So we're going to ignore these searches. We don't even look at the values. We see, okay, this value is greater than this one, so we're not going to go down this path. We know this is a good path. So these values get passed up. Now we're going to search down this one. We see a 5 here. And then we see, okay, we're going to do the minimum value, so we got a 2. And so in this case, 2 is greater than 0. And so we're going to ignore the paths, these paths here. We're not going to search under them because looking at the top beta value is less than the highest alpha value you have. So you need to keep track when you're doing this of both the alpha values, which are in the green rows, and the beta values, which are in the orange rows or the brown rows. So this 2 gets passed all the way up. Now we see here that 2 is still greater than 0, so we're going to ignore these rows. And then when this value is going to get passed up. Now we're going to this path. We see 5, and then we see it gets 1 because that's the minimum. The 1 gets passed up here. We see this is -3. So this value, the -3, is less than this value, so we're going to ignore this row. Basically say, okay, we can't get any worse than this one. Oh, we're not going to even check. And so we're going to pass up the ones this way. Now we see we have a -5 here. -5 is less than 1. And so we're going to ignore this row. We're going to pass this up. We see -5 is still less than 1. So we're going to ignore this path. And then we have 1 this way. And then we see all the way down to here we have a 2. And so we can see that this is probably the best path we want to take because we can get a 2 value down here, whereas these other paths, the scores are all pretty low. And so what do we gain by doing this pruning? Well, worst case, if we don't basically prune anything, we're going to get a big O of b to the h. So b is the breadth or the number of branches. So in this case, it would be 2 to the 5. The best case is basically get rid of half the nodes, so we have b to h of 2. So basically, it's kind of reducing the exponentiality of the data, but it's still going to grow exponentially. And so, kind of as kind of food for thought, so if you want to pause this and think about this, in which order should the nodes be examined in order to achieve the best gain? And then kindly, we kind of talked about the alpha beta procedure, kind of going over the basic values. So the alpha of a max node is lower bound on the backed-up value. So remember, the alpha is the lower bound of the max node. The beta of the min node is the higher bound of the backed-up value. And the updated alpha beta of the parents of the node was when all the searches below has been completed or discontinued. So remember, if the alpha above it is less than or greater than the beta below it, then you don't go down, you discontinue that search. And since we already talked about the alpha beta search, I wanted to go over kind of just the TicTacToe game you're going to go for your homework 5 for this assignment. So there's 8 classes within the code I've uploaded on the website as well as on the GitHub page. We have alpha beta, which is holds basically just the alpha beta information that you're tracking. The board, which basically draws the board. We're using swing to do drawings. We have game, which is the driver and renders the game. We have a human player and a machine player. We'll go into machine player a little bit later, but basically this is where you're going to do the bulk of your code. And then we have move, and which basically tracks your move. And then we have an abstract class of player that's basically the parent class for human player and machine player. And utilities, which basically just calculates the min and max values. And so I'm going to run the game, and then we'll go into and then I'll go into machine player to show you where you need to update the code. And so basically we generate a board, and then if I pick a spot, it's going to draw the X there. And then right now the machine just randomly just randomly picks a square that's open to put an O. And so notice here, if we're using adversarial, it would probably look at this spot here to put the value, and you can see I win. So with the random one, you'll almost always win. What you want to do is make the computer smarter so it can attack you in your tic-tac-toe game a little bit better. So I'm going to kill this, and then I'm going to jump into machine player. And you can see here, we put essentially a 1 second delay after you click to run it, even though it can run it automatically. And then you can see it picks a spot randomly times the number of open cells, and then just basically calculates where to put the move. And if it's a legal move, if it's not a legal move, it'll basically increment until it finds a spot to put it. So this is a really dumb logic. So the bulk of your changes you'll do for homework 5 are going to be in machine player in this location. So now we're going to go into variations of the min-max values. And so there's also multiple variables in min-max. For this assignment, you basically only have to do the alpha beta, but there's basically we can do is set aside a certain amount of time for each move. So this is if you have a time critical, like real-time AI performance. For those cases, basically if you're time limited, if you search too shortly, you'll finish early. So basically you want to maximize the amount of time. And if you search too deeply, you'll run out of time. So basically what you do is you give yourself a time slice, and then keep on running until you run out of time, and then just use whatever the best move is at that time. You kind of think about this when you see like when you have a lot of time to think about something, like say you're driving and you see a car way far away, you say, okay, well I pass it, I'm going faster, will I pass it, stuff like that. As opposed, and you can make all these different decisions. Whereas if a car just pulls right in front of you, basically you just swerve based on whatever the best option is you can immediately see. That's kind of what the time limited variations are. And so for this game, basically the idea is the two-player game. The domain is where the action models are inserted. Basically, another agent is modifying the environment as the game is going on. And then so you want to make the optimal decision as the case where you can do if you have the worst case. If the opponent plays a perfect game, that's how you want to move your decision towards that. And then some of the evaluations we use is the min-max procedure, What you want to do for your assignment is the alpha beta procedure, and then also I talked about a few variations of min-max. So again, here are the acknowledgments. I want to thank the code from 15 years ago from Stanford, as well as AI instructor resources. If you want to click on those and look at more stuff, you can get a better knowledge of this. I hope you enjoyed this lecture, and we'll have another one. We watch the other one, you can hear my wonderful voice.